Hello everyone, welcome to this lecture on logic gates. First, we will define a signal. A signal is a time varying voltage or current that carries information. Signal can be of two types, analog and digital. Analog is continuously time varying signal, example a sine wave, and digital permits only two levels, that is high or low or on or off. It has actually a pulse kind of thing, high, low, low, high, so on. Here we can see the representation of analog signal. You can see it's a sine wave, it's going like up and down, it's sinusoidal nature. In digital we can see that it goes 0, then 1, 0, 1, no intermediate states in between. Like this, in this analog signal we have 0, 0.5 maybe, 1, again 0.5 suppose, but here we have 0, 1, so on. Moving on, Boolean algebra, it deals with the logical statements, and truth table is a table showing all input and output combinations of logic gates. We will be discussing this in detail soon. Logic gates, well, logic gates actually, as it sounds, it's a gate. It's a gate for the current or the voltage to flow. It's a digital circuit that follows certain logical relationships between one or more than one input and output. We have several inputs or even a single input, and there is one output, and it follows certain rules to define whatever happens to the output. There are different kinds of logic gates. Example, OR gate, AND gate, NOT gate, NOR gate, NAND gate, or even XOR gate, XNOR gate. Here we can see we have our OR gate with us. We have taken two input OR gate. This is the symbol of the OR gate. You can see this is the symbol, and we have two inputs, namely A and B. Alright, and we have one output here. If we represent it as a circuit, we can see this one. This is a battery, this is a bulb. Now, to light this bulb, to complete this circuit, there are two switches, S1 and S2. Any one of these switches. Okay, let's consider this as A and B. That would be a better example. If we, close this switch A, the circuit will complete and the bulb will glow. If we complete this switch, the circuit will again complete, although A is open. Or even both. If both the switches are in closed position, the bulb will glow. If none of them are in closed position, the bulb will not glow. So this is the truth table. Let me change the color. The truth table here. We have inputs in one side and output in the other side. So here, see, there are two inputs. We are considering two input truth table right now for this OR gate. If both the inputs are 0, suppose both the gates are open, none of them are closed, circuit is broken, so the bulb will not glow. So we'll get output as 0. Suppose input A, that is switch A is closed. Alright, switch A is closed, but B is open. So 1, 0, the circuit is completed. You can see the bulb will glow this time. So we have output as 1. Suppose another scenario, A is open but B is closed. What will happen? The circuit closed here, bulb will glow. Okay. so we write this as glowing. Now suppose if both the switches are in closed position, that is the circuit is completed fully, bulb will glow. Either you complete a single switch on or both, no matter, the bulb will glow. So this is the truth table for the OR gate. You can see for 0 0 we have output as 0, and for 1 0 we have output as 1. For 0 1, for the output we get is 1. For 1 1 we get 1. A simple trick to remember is, if any of the inputs have 1 in it, yes, any of the input has 1 in it, the output will be 1. If none of the input have 1, the output is going to be 0. Moving on. Next is AND gate. So in AND gate, this is the symbol. You can see, you can draw this symbol, and we have taken again 2 input AND gate. We could have taken 3 or more, but we are taking right now 2, A and B. Okay. Now what happens if let's consider this as the circuit. Okay, there is a similar bulb, but the circuit this time is having A and B switches in series, not in parallel like the OR gate. In series, you have to switch both the switches in a closed position so that the bulb glows. Otherwise the bulb is not going to glow. If we put the switch A in closed position but B remains open, the circuit is not closed. Or the vice versa, B closed, A open, nothing's gonna happen. Or both open, nothing's gonna happen. Both needs to be closed. Both needs to be closed to make this circuit work, to make this bulb glow. So we have inputs A, B and Y here. Considering 0 0, the output will of course be 0. Both the switches open, nothing's gonna work. Okay, now 0 1. For 0 1, considering A is open and B is closed, still nothing's gonna work. So 0 1 0, as I said, nothing's gonna work here, as if we open this and close this, or vice versa, the same thing happens. Now the fourth and the last case, if both the switches are in a closed position, the circuit completes and the bulb glows. So if both the switches are on, the bulb will get on. Okay. Now the third one, the NOT gate. What about the NOT gate? NOT gate is a gate. We can see that the symbol is here, and the gate has an inverting nature. We also call this gate as inverter gate. We have this single input A and single output Y. See, this bubble means inverter. Okay. Now what happens? See this circuit carefully. If we put this switch to closed position, if we close this switch, the circuit will complete like this. The current will pass from this end. It will not go here. So we to lit this bulb, we need to remain open this switch. So if the switch, for example this is A, if the switch is 0, that is open, the bulb is glowing. But when we close the circuit, that is 1, the bulb will not glow. You can see the inverting nature. So if we want the bulb to glow, we will need to put the switch in open condition, so the bulb will glow. And if we close the switch, make this circuit complete, current will not pass through this path and bulb will not glow. Now, if we have NOR gate, this is a new kind of gate, NOR gate. It's called a composite gate. What is a NOR gate, basically? Well, NOR gate, we have OR in it and N for NOT, and we know the OR gate. So, consider it like a OR gate with A and B inputs giving an output Y. Now, take the output Y and use the inverter with getting Y bar. This is the NOT gate and this is the OR gate, which together makes NOR gate. The symbol for the NOR gate is like this. And we have the equation as this. Now, what would be the truth table for this gate? Okay, I'm drawing a truth table here. I'm drawing for both the OR and NOR gates to tell you the difference, but you need to draw only the NOR part. Well, this is the input part, this would be the NOR part, and this is the OR part for your sake. For inputs 0, 0, the OR gate, first we will be making the output for the OR gate. We would get 0. For 0, 1, we would get 1, 1, 0, get 1, 1, 1, we would be getting 1 again. So if we use inverter on these, all the outputs from the OR gate, right here, we would be getting 1 and 0, 0. This is the output of a NOR gate. Now, moving on, there is NAND gate. Now, what's it? This is a AND gate and an inverter. So, the symbol comes to be like this. So, what happens at the truth table? We studied the truth table for the AND gate right now, and we will be making it AB. This is the output for AND, and this would be output for NAND. You need to draw output for NAND only, not this, only this. For 0, 0, 0, 1, 1, 0 and 1, 1. For 0, 0, what would be the output of an AND gate? AND gate. For 0, 0, we would be having 0. 0, 1 also we would be having 0. For 1, 0 also 0. Both the inputs are 1. We would be having 1 here. Now, there is an inverter here. So the inputs would be inverted, like in this case. So we would be having 1, 1, 0. This is the output of the NAND gate. What would be the equation or the Boolean expression for the NAND gate? Well, A dot B for the AND and a bar over it. Let me remind you what would be the expressions for OR gate: A plus B, AND gate A dot B, and NOT gate A bar. Okay, let me show you some examples for solving the questions. Well, let's have a question here. We have X. this is Y. The output is Z. Well, X has two inputs, A and B, and from A we have an input to the Y. If we have 0 at A and 1 at B, what would be the output Z or Z? Well, if we have 0 here, the output of a NAND gate when we have 0 and 1, if you can see here, for 0 and 1 we have output 1. So we will be having output 1 here for X. For Y we have 1 and 0. What would be the output of an OR gate when their inputs are 0 and 1? As I have already told you, if there is a 1, the output is going to be 1. So the answer is 1. This kinds of question may appear in your examination. Let me give you another question similar to this. You solve this question by yourself. This is Z, this is Y, and this is NAND gate, this is AND gate. Similar kind of question I'm giving you, A and B. I'm giving input as 0 and 1. What would be the output? That's all for this lecture. I'm signing off with this. Do like the video, share the video, and subscribe to our channel. Thank you.